Let's continue our class. In Tuesday, we have learned the basic concept of external flow, right? Basically, if you look at it, the basic is very simple. Let's say you have a box. When the air is coming from here, you get the drag due to pressure. So this one is positive pressure. This one is negative pressure. It's as simple as, you have something like this. When the air is coming, of course, it will deflect because the pressure over here is higher than the pressure on the tank. It's as simple as that. But this deflection is, if it deflects, it means the pressure will be released. But if it's stiff like this, if you do that, the stronger the wind, you will find the more forces is needed to hold it, right? The more forces is needed to hold it, which means the pressure difference will be higher, so the drag due to that pressure will be higher also. On top of that, so this one, if you look at this, it is F drag due to pressure, but since you have this also, right? In this case, the area is the frontal area, right? Whereas if you are looking at the top of the plate, here and over here, there is also a shear, right? This shear will provide FD due to friction. Okay. In this case, this one is the coefficient of drag due to the pressure times half rho phi square. This one is your dynamic pressure. Okay, this one is your dynamic pressure. And you have the area. In this case, this area is the frontal area. Okay? Whereas in this case, it is CD due to friction. Sometimes it is called CF. Same. CDF and CF is the same. That's why in your boundary layer approach, it is written as CF rather than CDF, right? So you have CDF. Okay, and of course you will have half rho phi square. Same, this one is the dynamic pressure. But you have this A. This area is not the area. This one is the surface area where the friction is working on. Okay, in this case, if you are having this book, this is the first time I bring this book to this class. Okay, this is your frontal area. Okay, guys and girls, this is your frontal area, whereas this one is the surface area, the friction area. Okay, the friction area actually is this one, that one, and that one. If you want to consider all, if you are having a flying box, right? If you are having a flying box, actually, if I ask you what is the power needed to overcome the friction drag, you have to take into account this, that, and that. Right? Because all of this surface will be having a drag. Okay, so that's about it. But then in the next lecture, what happened is we combine this and that, so it becomes CD only. CD is CDP plus CDF, right? If you remember. Most of the time, there is cases where this one is minimum. Sometimes this one is minimum, sometimes this one is minimum. Okay? In the case of, in your tutorial, in the question 1, there is air coming from the side of the sideboard, right? The side of the sideboard. Most of sideboard is like this, right? It's thin. So the frontal area will be marginal. So you don't care about the frontal area, but you care about the friction working on it, right? On that case, CDP is 0, so you just consider the CF. So you calculate the Renault number, you get whether it is laminar or turbulence, you calculate the CF, you can calculate the drag force working on this board. But what happens if the air is coming from this? It's totally different. Okay? Even worse if the air is coming like not perpendicular or parallel but at some angle, right? And this. So what you need to do is you need to split the flow. Okay, one velocity from the perpendicular direction, the other velocity from the tangential direction. So from the tangential direction, you can calculate the drag force due to the friction. From the normal, you can calculate the drag force due to the pressure. So you can do that. It's not a big deal. Okay. So let's recap. This is what we have. You have the drag coefficient, and later on you will have the lift coefficient. Okay. The lift coefficient, the area will also be different. This one will be the planform area. Okay. I will show you what is planform area later on. But if you are having this area is the frontal area. So when we are looking at the car, this is your frontal area, right? Or this one. When you are looking at the truck, this is your frontal area. So it doesn't matter how long the truck, right? As long as it has the same cross-section area, that's your frontal area, right? So whether the track is attached to the trailer or it is not attached to the trailer, the calculation will be based on that. Okay? But of course, when you have a trailer attached to this thing, it will be different. You are looking for your goal. So, okay, so I have shown you this yesterday. When you are having a parallel plate like this, most of this contribution is due to the friction. If you have the normal perpendicular like this, the contribution is due to the pressure. If you have a cylinder, then both of them, cylinder or streamline. Okay, and if you remember on Tuesday, I told you why nowadays car looks like this shape, right? It's getting slimmer and slimmer, more streamlined. It's because they want to minimize the drag force. Okay? Why don't they do this in the earlier generation of the car? Because at that time the manufacturing technology is not as advanced as now. Okay? Nowadays your car is made like a tin Milo, right? Last time if you have somehow your grandparent is very rich, okay, if your grandpa is rich, you will have your parent or grandparent having a car, right? If you do this to the body of that car, you will know that it will be very thick, right? Because at that time this plate is made like, okay, you have the plate, then you bend it, you form the car. Nowadays it is not like that. It's molded. So the liquid metal will be, injected to this mold, and then you get those cars, right? Honda got G-Con whatsoever technology, right? Proton has HPF or something. So it's basically like that. That's why with the advanced manufacturing now, you see that the skin of your car getting thinner and thinner, right? Some of the car, if you push, you will feel like your hand is swollen by the skin of the car. So that's why nowadays they can do that. They can advance manufacturing it such that you can have that one. Okay, if you are frequent traveler and you take a Boeing 787, the aircraft is made mostly from the polymer. Even the wing is not metal, right? The wing is made from polymer. So that's why you get all those shapes. Okay. Okay. Now, yesterday I told you that the drag can be two-dimensional when it is very long. Right? When you have you see this column in front of this building, there is a column that holds the roof, right? Okay, for that kind of column, because the length is much larger than the diameter, okay, the ratio between the diameters and the length is very big or very small, if you are talking the diameter and top. So you can look at it as a one-dimensional, which means you can cut it and take the cross-section only, then you can calculate the friction. But if you are talking about this PowerPoint remote control, right? This one is not long enough. So you cannot neglect the effect of those sides. Okay, in this case, you cannot approach it as a 2D cases. You need to approach it as 3D. Okay, but luckily, if you look at it later on, someone has done the dirty job for you. So they have done all the experiment, blah blah blah, and develop a correlation for you. So we will just use this correlation to solve our problem. Okay.